इसमें एक्चुअली सीधे भी जा सकते हैं यूट्यूब पे मोर से।
अच्छा,
हाँ, तो मोर में जाके सीधे लाइव ऑन यूट्यूब, तो वही करता हूँ मैं, कस्टम वाला नहीं यूज कर रहा हूँ अभी।
ठीक है, ऐसे कर लो।
कस्टम वाले में प्रॉब्लम हो रही थी।
सभी ऐड किए हैं क्या ये आपने?
हाँ, अभी कर दिया सारे ऐड।
ठीक, चलो मैं उनको कॉल करता हूँ स्पीकर।
ओके ओके।
ठीक है।
हेलो।
हाँ, हेलो।
या डॉक्टर नीरज।
हाँ, यस।
प्रोफेसर घोष इज अराउंड नाउ।
हाँ, राइट, ही इज ऑन। We still have 3-4 minutes. Meanwhile, you may please check for YouTube streaming. Okay. And
Yeah.
let me ask Professor Ghose for sharing his presentation.
Okay.
Professor Ghose, can you hear me?
Yes.
Okay.
What about you?
Yes, it's okay.
You
We can
hear me?
hear. Yes, we can hear you, and
Okay.
as well we can see your video. So now you may please share your screen. We'll start in a while. Yes. Fine. Yes. Now we can see your slides, and some of the participants are still ready. So we'll start in 1 or 2 minutes. Okay, sir.
Yeah, yeah.
Okay, so good afternoon, everyone, and good afternoon, Professor Ghosh. Yeah, we are here on this second talk of the final day of the webinar series on experimental and computational tools for materials research. And we have Professor Ghosh from RRCAT Indore to deliver his kind lecture. I request Dr. Neeraj Jaiswal to kindly introduce the speaker formally. Please.
Okay. Thank you, Dr. Ispal. We are fortunate to have today with us Professor Ghose from RRCAT, and he will be delivering his talk on density functional theory, basics and applications. So let me introduce Professor Ghose. He did MSc in 1990 from Visva University, Santiniketan. Thereafter, MPhil in 1991 from Institute of Physics, Bhubaneswar. Professor Ghose is also the recipient of Young Physicist Colloquium Medal 1994 by the Indian Physical Society, and he did his PhD in 1997 from Institute of Physics, Bhubaneswar. He was also served as the guest scientist at Gerhard Marketer University, Germany. Then he did several postdocs, including 1997 to 1991, 1999 at Federal University, Rio de Janeiro, Brazil, and the next was Department of Physics, University of Arizona, USA. Then he joined as assistant professor visiting at IIT Kanpur from 2000 to 2001. He was also at Max Planck Institute from 2007 to 2008, and then as a visiting assistant professor at National Center for Theoretical Sciences, Taiwan. He was serving as Scientific Officer E from 2002 to 2008 at RRCAT Indore, then Scientist F from 2008 onward, and presently he's serving as Scientific Officer G at RRCAT Indore. He's also at the referee board of various eminent research journals, including Physical Review Letter, Physical Review B, College State Communications, Physica C, etc. His area of interest is magnetism, superconductivity, and correlated electron system. And he has about hundreds of publications in international journals and reputed conferences. So we are really fortunate to have Professor Ghose with us for today's talk. Now I would like to request Professor Ghose to start with their talk. Professor Ghose, please.
Thank you, Professor Neeraj. It is really a pleasure to give this talk, which is arranged by IIT DM and Central University of Rajasthan. This is it's an honor for me that you have chosen me for this talk. What I understand is that the participants are from different backgrounds. So I understand that some people will be MSc and some people from humanity and maybe starting PhD. So I have really starting from the zero, assuming that we don't have access to any journals or books. So we will go from basic understandings and try to arrive at the density function of material, how one performs density function theory. And congratulations that you are Is everything okay?
Yes, it's okay.
So,
We can hear
so,
you.
so the first slide that you are seeing, my name is Varman Ghose, as was told by Professor Neeraj. And the building that you are seeing is a bit curvy, as you see. So this is a accelerator. This is a famous accelerator building in which I sit. Today also I'm talking from my home. This is a 2.5 GeV accelerator with 200 milliampere current, and this has been used for various condensed matter material science experiments. There are about 20 beamlines that are working, and many, not only from the country, but sometimes even from the abroad, people come to do experiments. And I personally sometimes get engaged with explaining their data. So if you are experimentalist and you want to do experiment, there are opportunities to come here and perform experiments. Sometimes your data are also analyzed. Okay, so for details, you see the online pages. Okay, let me start the talk. Okay, so what is actually the problem for which we need density function? That's the point that we have to first understand. So, as you know, this is a tool for materials. Materials could be anything. For example, it could be a solid material, it could be some biomolecule, or it could be a metal, semi-metal interface, and so on. The point is, it becomes a many body problem. It is not a single body or two body problem. It is a many body problem, and there are almost no proper tool that can give an exact answer to the many body problem. We will see that even exact answers are there available. Suppose somebody gives a solution, we are not being able to use that solution. We'll see that. Because of that, we need density. Try to follow this in a few of my slides. Okay. So, as you can see, very vaguely, without any structures or symmetries or anything involved, we can very vaguely, crudely take material as collection of. I cannot see some of them. Materials I can take as collection of nuclei and electrons. Okay, so this is indeed a many body problem. I will overemphasize this many times that it is a many body problem, and the only thing that we know we can do it by hand analytically is the solution of hydrogen atom problem, which is, as you know, that these electrons and nuclei are quantum particles or subatomic particles, and their dynamics is described by quantum mechanics, and they are basically dealt with for interpretation like this. This we can solve for single particle because the hydrogen has a one proton and one electron and nothing else. And its solution comes like orbitals like this. You can write its energy value, which is proportional to 1.3 square, 13.6 square, right? This much we know. So
sorry to interrupt you, sir. Your volume is quite low.
Yes.
The voice is quite low. So if you keep your if you could please keep your mic near your mouth, that should help.
Hello.
Yeah.
Now it is okay.
It appears better. And there is one more problem, sir. The audience is seeing another window coming up on your slide. So it says about. So do you have any other window open right now, other than Zoom? And,
it says 8 people haven't. Oh,
no, it's not about Zoom. It's on your PC. Do you have any other window open, which is coming over Zoom window? Yeah. So if you close that, we won't be seeing the other window.
Now is it okay?
It seems okay, sir. Yeah. It seems okay, sir.
Yeah. My screen is partially blocked by some things that are coming.
Okay. Is it okay now?
For example, this thing are coming: mute, stop video, security, participant, 200, like this.
Okay, so I will then log the meeting. and that should
Yes,
help.
that would be much better. Yes.
Yeah. So is it okay, sir, now?
It is still there.
Okay. Yeah, it's okay now, sir.
Now it is on up. Yes.
Okay.
Yes. So I will have another request is that maybe maybe it will take a little bit more time than allocated because and there could be some problems like this, and also I go really slowly so that in the beginning.
Okay.
But I will not take too much time.
Okay, sir. Please go ahead.
Okay. So what so far, if I start from the beginning again because many people did not. So all I said so far is that we are dealing with real materials. The real materials could be solid state material, it could be liquid, it could be, for example, some nanorod, or it could be interface problem. Okay, again, those things are coming and going. Sorry. Is there a mistake? Can you hear me?
Yes, sir. We can hear you, but your slides are not visible. Please share it.
What should I do?
Not yet. Yes. Yes. Now it's visible.
Yeah. So my corner is always covered by that thing.
Okay.
That's why I click someone and
Now it's okay, sir.
yeah,
Please
it is
proceed.
better. All right. So we do not know how to handle many body problems. Basically, there are no tool that that exactly tells us the exact solution of that. And we are going to see, we assume that even if someone tells us the exact solution of the memory problem, still we will not be able to deal with it in the wave function method. Okay, so hydrogen atom problem everybody knows that I expect. Okay, so let us talk about, yeah, again my slides are blocked.
We can see it, sir. It's
No, I
visible.
cannot see.
Okay.
I cannot see something. All right. Okay, so how does a many body wave function look like? Nobody knows actually what should be a many body wave function. But let us keep it simple. Let us take three electrons. The wave function must be the function of three coordinates of the three electrons. You see, first the problem is we do not know, we do not see electrons. We cannot see electrons. Do not treat electron as particles, first of all. That it is here, R1, R2. They are somewhat, they're distributed, they have profiles. That is what is wave function is. Okay. And the wave function distribution of three different particles at a given instant, let's say, we must contain the arguments R1 and R2. Assuming that the particle number 1 or electron 1 is at point R, then the joint probability of this such a state that contains three electrons would be given by this. Probability of the particle 1 at R is capital psi mod at R R2 3 mod square, in which we integrate out the other two variables. That gives a probability distribution for finding the electron number 1 at position. Okay. Similarly, the same exercise you can do for R2 and R3. That is the electron number 2 or electron number 3 at position R. Okay. And because the electrons are indistinguishable, we don't know which electron is what, and they are completely indistinguishable, and there are no other effects. In that case, all these probabilities are identical. and they add up to what is called the electron density. So this is a simple example for three electron system, and the total density distribution will be given by G, which is number of particles that are constituting the majority of motion, times the mod square of psi r r2 r mod square, where it is indicated the integral variables are r2 r. All right. Okay. In general, below this orange line, if you have n particle system, that means you have n nucleus and n electrons, let's say. All right. So in general, the wave function will have all the coordinates, including uh, that of the nucleus. Okay. In general. So the following the above. Sorry. Following the above prescription that I have done in the upper part of this slide, the probability of this many-body state of finding the electron number 1 at a position R is given by this. Okay, and in similar fashion, we will get the density distribution by adding all the probabilities. Okay, and assuming that all the probabilities are equal, the density distribution, the way to find this density would be given by this. All right, which is not very easy to find out, but such that the total number of particles will be given by this equation. The integration nr dr equal to n. Okay, so I'm trying to point through this pointer. Okay, all right. So through this slide, we have learned how to calculate density distribution. Given that a wave function is given, we do not know how the wave function is. How to calculate that wave function, we will find out. Okay, and we'll see that this is the all the okay, all right. So we have so far learned how to calculate density distribution of a many-body system. Now, how do I get the electron wave function? I have to solve something called many-body Schrodinger equation, right? And the dynamics will have kinetic energy as well as the potential energy. Okay, and as I told that the electrons and nuclei are quantum particles. So in general, the kinetic energy is written as v square by twice m plus potential is denoted by some Vr times psi r is equal to total energy E psi r. Okay, this is the construction of the Schrodinger equation. You can construct this from Newton's equation of motion when you assume that these are not definite. Means this you have to treat as operator, momentum or potential. You have to treat them as operator, and P is replaced as minus I is equal to. Okay, and if you just substitute this here, you get this Schrodinger equation. Okay, if you do not know how to derive Schrodinger equation. All right. So the kinetic energy for nuclei and electrons are given by this expression, which is minus h square by twice AE E for electron and del I square. This is the kinetic energy for electrons, and similarly, this is the kinetic energy of all the nuclei, and all the number of nuclei are summed. All right. Okay. So in general, this is the kinetic energy expression. Similarly, the potential energy, which comes from the electron-electron repulsion, is Coulombic in nature. Classically, you know this is this. All right, but we have to convert that into operator. So these are position operator, and the symbols are the usual meaning. This is the charge of the electron, and this is the in the vacuum of the polarity. And similarly, the nuclear and nucleus repulsion energy. Nucleus also have positive charges, and they are replaced by this, which is also like total charge square by the distance or separation between the nucleus, and nuclear coordinates are represented by the capital R's. Okay? Whereas the electron coordinates are represented by this. And then what is left out in a system of many bodies is the electron nucleus attraction. Okay, because of attraction, this interaction sign is negative in front of this sound. Okay, all right. And so this is the small ri minus capital Ri is the separation between the between the nuclear and the electron. Okay, and this is the nuclear electron nuclear attraction. So if I add up all these terms and put it here, I shall get the many-mode circular equation. All right. I hope there is no question for this. If there are any questions, please ask the organizer and ask the questions. These are done in MSc courses. So, okay. So this is what I have done. I have added up all the terms and I got the many-mode circular equation, which looks like this. All right. Now, first of all, we do not know how to solve this equation. It is almost impossible to solve this equation. But even if we can solve this equation numerically, let's say, we are going to make lots of mistakes. Why? Because these quantities, h bar square, etc., are very small numbers. Okay, given here, I have given it in this screen. Okay, and so you first, before making any solution, try using solution in your any equation, not only this one, equation, you see that your parameters must have good value. May not be very small or very large. Okay? Then you have to think about it. Okay. So we convert this into something called Hertz. Okay. So these are the very small. Okay. So this one it talks about this equation m square by a naught. A naught is Bohr radius, the smallest distance between the nucleus and electron in hydrogen atom. Okay, is equal to the electrostatic attraction between the nucleus and the electron. That gives you the stability of the atom on the system. And in a stable orbital, angular momentum is given by mdA, which has the dimension of h bar. All right, and that gives you this equation. All right, and interestingly, the kinetic energy is also expressible in terms of Hartree energy. Where Hartree energy is defined as E square by 4 pi epsilon. Okay, so we divide everything by E Hartree so that it becomes dimensionless. So the right side is E total by E Hartree, and a small manipulation will give you this. Okay, and so in the next slide, the Hartree atomic units are defined like this: masses in units of Me, which is electron mass. That is, Me is equal to 1. Bohr radius is equal to 1. Bohr radius, I guess you know, it is around 0.5 nanometer. And then the energies in units Hartree. This I find in our last slide. Okay, this is also the energy 1, and in that case you get this equation. Okay, the same equation written in terms of Hartree. Okay, please derive this if any step is you cannot understand. These are doable, very simple. Okay, the point is that it looks clean. Okay, so the earlier equation, this or this was this elephant, which is not saved, which looks very dirty. Anybody saw in the equation, and after I saved, means I express in terms of Hartree units. That is, then it is like just like a saved elephant, but it is as heavy as earlier, and we cannot still solve. Okay? But anyway, it is important step to clean it, yeah? Because at least the numbers are not so small. Okay. Now, next question is, how do I solve the problem? Okay, how do I solve this memory equation in Hartree units? Okay, let us see. So first slide I showed hydrogen atom. If I do not have any interaction, then I know how to solve equation. So everybody started thinking, can we write this many-body Schrodinger equation somewhat similar to Schrodinger equation of hydrogen atom, so that we can write solutions. Okay. So let us see what can be done. So before I go to the density function of fluid, I will ask the audience that there are many other manifold techniques that are going on that actually started even much before density functional theory. All of them are partially successful, and of course, obviously not completely successful. And you should know that also, because I mean, that's how you have the feeling for the whole condensed matter system. So, one of the many body techniques is known as quantum Monte Carlo. Okay, I personally have used this method earlier when I was in Brazil, and we published a report. Quantum Monte Carlo method is one of the finest methods. You know, it is, you can solve model, you can start from ab initio, but it is very expensive, very expensive. Even in this paper, we could do only for 64 sites, and there are many various problems. All famous negative sign problems is there, and that means you cannot go for any parameters and etc. Okay, so even in the development of density functional theory, quantum Monte Carlo has played a very crucial role. I hope I will have some time to talk about that. There is something called exact diagonalization. You know, Hamiltonian is nothing but some form of matrix. Okay, and to a finite size, you can exactly diagonalize. It is not so easy as I am telling, but in certain cases it is possible to solve. Okay, and we have done some work. I mean, I have done many works on that. Some of the works are done with experimental experimental works, and they are published in physical review. One can see the exact dimension, which is exact technique. It is exact technique, uh, but to start with, we already compromise with many workflows. We do not take all the interactions into account. We cannot do the, I mean, in this work, why the whole solid SR2CU is treated within 12 sites. I could go only up to 12 sites. So, even if my work is being appreciated by physical reviewer, but I know in my heart that solid state is not 12 sites. Okay, solid state is infinite lengths. All right. So they are exact, correct, but they have many problems. You cannot do, or real length problem is there. Okay, real material has it is infinity and you cannot do it. Okay. Then there are perturbative manifolding. For example, I'm going to discuss a little bit of Hardy-Fock theory. Okay, and then you can add Hardy-Fock, you take as the zeroth part of the Hamiltonian, and you can perturbatively add excitations. Okay, even there are problems that you cannot go to, for example, very huge site. Okay. So, but configuration interaction is a very well known method. This is also very similar to couple cluster method. Okay, so they are very similar. I have done this also. Why I'm telling this? A person who already dealt with so many techniques now doing density functional theory. That means you should take that as a motivation that density functional theory has a point, and I'm going to tell that. The configuration interaction can be applied to organic systems, other metallic systems also. There is something called Green's function and Feynman diagram technique, which partly you can do by hand. You can do analytically. Okay, Feynman has was a different brain. He could draw the diagram for a particular interaction and its results in terms of the Green's function, when you know the value of the Green's function for a non-interactive system. So in each case, if you see, uh, but they are you already compromise. It is a model Hamiltonian, means you do not take into account the core electrons, the other electrons. You take only very few electrons. Okay? And for example, I am interested in superconducting, for example. And whatever technique I do, if I go only 12 sites, it does not make sense, because the coherence length is about few angstrom, means even high TCA superconductors, it is a 50 angstrom. and that will be 1,000 atoms. Okay, if you take a cube or a circle or a sphere. Okay? So, I mean, the long range order that is supposed to be covering, that will not be there in this kind of approaches. Although theoretically the results are exact. Okay. So similarly, you can do model Hamiltonian, and I have given some references. You should see that. These are the technique other than the density function theory that we are going to talk about. So, all right. So I shared at the beginning that even if someone gives me the exact wave function, I will not be able to use it. So let us take silicon for example. Silicon electronic configuration of silicon I have given, which is like this, 3s2 3. All right, and all others form a close. So even if I do not take these electrons into account, you see, yeah, there is a question from Pallavi Shukla. Hello.
Yes, sir.
Yes, we can hear you, sir.
Somebody raised hand. It showed in my screen, so I stopped. Okay.
Yeah.
Shall I continue or?
No, no, you please continue. We'll take queries at the last.
Okay. Thank you. Thank you. All right. So, wave function uh, is a profile of electrons on many electron systems, right? So first of all, you got to actually make grid and try to find the value at different points in three-dimensional space, right? So let us take, I take the X grid as 2 times the Bohr radius, which is about 0.1 angstrom. The lattice constant of silicon is 5.43 angstrom. Okay, so the and silicon is in FCC like this. So its volume is a cube by 4, and the small value of is delta x cube. So that gives me the number of points in the grid that I have to take, or there I have to make the wave function value I have to make at 40,000 points. And there are 8 valence electrons per unit cell because there are 2 atoms per unit cell of the silicon in the diamond structure. And therefore, the psi will contain 40,000 to the power 8 complex numbers, which is 10 to the power 26 terabytes. So even if I have taken already compromised wave function of only 8 electrons, okay, it is 4 into 2, 2 atoms. Okay. Still, you see, I have to make a storage of the wave function, which is of the order of 10 to the 26 terabytes. Because you got to calculate anything, total energy or momentum or any physical property through this kind of expectation. This is the quantum mechanics we do. So for that, first you need to store this, which is almost impossible in this stage. Okay. So the first step to make simplification to the many-body Schrodinger equation is to something called Born-Oppenheimer approximation, something similar to Born-Oppenheimer. I am going as a simplified Born-Oppenheimer approximation, in which one treats the mass of the nuclear heavy compared to the that of the electrons. Okay. In that case, this number would be very, very small. So I have cut this in 5 red line. And similarly, this term, which is attraction by the repulsion by nucleus, okay, this term will be just a constant term. Okay, because in the electronic, we are looking for the electron function or electronic state. It does not contain any electronic coordinate, and therefore I will have I can safely remove this term. It can be done much better way using Born-Oppenheimer approximation, and I assume that you know this. So the main problem of electronic structure theory would be to solve this equation. It is not easy to solve, although it looks like a very small equation to solve. It is next to impossible solving this equation because of this interaction, which is half 1 upon Ri minus Rj I naught. So this is a Coulomb equation because this part is one body, but this part is actually comes in pairs. Okay, and let us go to the next slide. So as I said that in the beginning, that for hydrogen atom we know the solution. Okay, so if I that make my Schrodinger equation, Meinrad Schrodinger equation look like hydrogen atom, that means I somehow I neglect this Coulomb repulsion, which I cannot do. I cannot do. I repeat, I cannot do this. But let us, for the timing, say that this Coulomb interaction is not there, then they are independent, right? So they are independent electrons, and therefore the possibility of different independent events will be product of would be product of, because the joint probability will be product of all the events, right? So in that sense, the wave function will be product wave function of the individuals. All right. This was the beginning of Hartley or independent electron configuration, and then I can allow this H0 Ri or Ri goes from 1 to n to apply on this unity of function, which is a product of okay. And so because this it will apply only to this H0 R1 will only apply to 5 R1, and H0 R2 will only apply to 5 R2 and so on. So and it will be given by their energy eigenfunctions are known because they are hydrogen light. In that case, I will get the total energy as all the total energy will be added up, and I get right. And if I consider normally, this is the way one just consider the epsilon 1 is smaller than epsilon 2 and so on. And then we fill up the levels like this. In this case, we have just done the independent electron configuration. Okay. What is the problem with independent electron configuration? We have neglected completely the electron-electron interaction, which is responsible for all interesting events. All right. So if I have a two electron system, the independent approximation, electron approximation, the density profile, the density that I have taught you in the beginning of the talk to calculate will be to integrate out the other coordinate and take the mod square, and because this is the number of the, and so it will be like this. So if I integrate out the R2, it will be independent of R2 and it will give me 2 pi R1 square, 2 pi R1 square. So even if I have two electron system, in this independent electron approach, the density does not have any signature of the secondary, which is incorrect. On the other hand, I could choose psi R1 R mod square, that assuming that the second electron is activation R. Okay, and then in a similar way, I could get 2 pi 2 R mod square. So the way I do, I get a different answer. In both the cases, the other electron's density or any signature is not there. That means there is something not correct. So what was not there is that we have not considered the harmonic nature of the electron. All right. So that can be done by anti-symmetrization of the wave function, which I assume that you know was actually done by all selected determinant. You can write the electronic wave function for the two particle like this, okay, and 1 by square root 2 is to take care of the probability, and the selected determinant is this, so that if you exchange spin and space coordinate, assume this R1 char R1 sigma 1 and R1 sigma 2, that is spin also, which is not written for sake of simplicity of the notation. And then if you exchange them, it should give me a sign minus sign. This is actually Pauli's exclusion principle. And in order to take this, you must have the wave function of this form. Okay, you must have this. this one. So if you use this, then you can again calculate the density, and you get something which is I1 R mod square, R mod square in the same prescription the way I have done. In this way, only you have to assume that I1 and I2 are also octable, okay, as quantum systems. And so in general, in this way, if I do for 10 electron system, the density will be sum over I naught square. In this, we have taken into account the all these expressions. Okay, so um, uh, even doing all these expressions, including all these expressions, we have actually removed the electron impact, right? So we have got something with density with a many body. So if you have a density and it is in needs of the charge of the electron, so you have basically charge density. So the many body electron coefficient have a charge density. So if you have a charge density, that must create a potential, effective potential following Poisson equation or Gauss's law, right? So that was the second thought, and then people said, okay, so this is the Schrodinger equation kind of equation in absence of many body interaction or the electron. So this N is for nuclear, all right. And so because this charge density can produce an electrostatic field, should we add this? So this is the, and this will be, this is we have done in our MSc classes, that this will produce a potential which is called RT potential, which is governed by this equation, very similar to Prof equation. Okay, so the solution of it. And this is completely electrostatic. Okay, this is electrostatic. In fact, this is classical. Okay? So this idea was incorporated and said that okay, so these i's are giving you some charge density that is in turn giving you electrostatic potential, and therefore we must add that electrostatic potential instead of taking the memory interaction at the beginning. We have already taken care of the electron interaction in some form, okay. But when we add this electrostatic potential, which is given by Hervey potential, so this is actually volume integral, okay. So this volume and this is charge density will give the total charge, which is like dq, and therefore the potential will be given by dq by r minus r prime, where r prime is the position of that charge density. So, at any position, put r, you will get the VA charge, which is hard potential. Okay. So then I will have a new eigenfunction. Okay. Because I have added new potential, it will give me new solution. Okay. So I will have new this. This will give me new charge density, which I will be able to calculate as I have explained earlier slide. Okay. So it will give me a new potential again. So this VA will be again modified, and so on. And this procedure is called RT self-consistent. Okay. So I mean, we have started with something in which we have neglected something, and then we again get back. All right. So this was the first step in the formation of density function of theory, which is called RT self-consistent theory. We do something very similar to this in here also, as we will see. All right. So next comes the Harty and Fock equation. So what happened actually? We have taken this independent electron solution and only the Coulombic part of the interaction. So Harty Fock said that okay, look, we know quantum mechanics that this is the way to get the energy of the system, and which is uses in Tate and Brown equation, and therefore it will be like psi star H psi, where psi will have all star will have all Q1 star, phi 2 star, phi 3 star, phi n star, and so on, and H will be the Hamiltonian that I had written without electron. And you can add electron as well. We added electron. And then we said this energy should be minimized, and therefore you take a derivative of this. This is called functional derivative. I will define what is functional derivative in one of the slides later. But apart from Hardy, what Hardy-Fock approximation two things Hardy-Fock theory is that they took care of the many-body wave function must obey this anti-symmetrization, which is probably the solution. And we said that this will give me the minimized energy or the ground state energy. All right. So this must be equal to 0 for stability. All right. But so you are actually varying the size. You are sorry, orbitals. Orbitals are nothing but the profile of the electrons, right? Okay. So if you change profile of the electron, that means you are considering some kind of motion of electrons, right? You are modifying the electron. So the other orbitals should also change. This is not done in Hardy-Fock theory. However, he said you are changing, but the normalization condition must not change. So you are changing phi's. So you will have all sets of this is I equal to 1 to n. All right. So you will have all these conditions, and this condition comes in the form of equation called this Hardy-Fock equation. Okay. This is you should derive it. It is not very difficult to derive, but today we cannot do this because that will take care of all our time. All right. So apart from these terms that we had in Hardy's equation, there is an extra term which is written in blue, which is Vx r prime phi I r phi. It gives me this solution, and this is called exchange potential. Why this exchange potential? Okay, and please derive this that this exchange potential is given by this. Okay, where besides J is all up to the occupied sides. All right, this comes because of the exchange, because you have taken the this kind of wave function which gives you the sign change in the wave function, and if you take that into account, you will get a extra potential which is this makes the life very difficult, but you must derive this because this deriving this exchange potential is part of the efficiency as you will see in few slides. Okay, if you cannot derive this, you can write to me. I will send you step by step derivation. Okay, so you notice that this already gives us some problem. This is called non-local problem. Means to find the potential at any point r, you also need to know its value at r point. Okay, and numerically, you need to find the value at r prime for r prime is anywhere, and then again for each r you have to do. So this problem will be n square level, not n. Okay, so numerically if you have many problems, we discuss this part. So this is called actually quantum electrons. That means you are taking into account the exclusion principle, and it introduces something which is non-local exchange potential of potential. So you have to solve this equation. This equation is the same as that Kohn-Sum equation. Very similar, not same. It is very similar. This phi have physical origin, it has physical meaning, but the Kohn-Sum equation do not have physical meaning that we see. So this is the strategy actually that is being followed in many work theory, including this theory, and we will explain what the special means. Even apart from this, there is something called correlation energy. Okay, using Hardy-Fock method do not take into account the correlation energy. As I explained while doing the Hardy-Fock theory, that when you take the differentiation of functional differentiation with respect to each orbital, you have kept all other orbitals fixed. That means there is no influence of electron repulsion. Because if there is a, it's like one electron is moving and other electrons are not being affected. Okay, so if that happens, that means you are not taking correlation into account. This is what is the reason in why in Hartree-Fock theory correlation is not there. Okay, so it has been said that so up to this much we have the medium, we have RT, we have exchange, we know how to derive, we know, and this is being put by hand. Okay, let's say if I can put by hand how to determine the correlation. So what is the correlation energy? Correlation energy is the exact energy minus whatever is you done with Hartree. Okay, so that will give me the correlation energy, and from correlation energy you can derive the correlation. Okay, and so this is how the Cohen-Sum equations are derived. This is the philosophy of deriving Cohen-Sum equation without deriving it properly. Okay, because now we have to go to density. Okay. So uh, okay, this slide is to show that correlation is important. Uh, uh, in the beginning, I told that the hydrogen atom problem that we solve exactly. But even if we solve two electron problem, which is helium atom problem, there is no analytical solution. We have to go to numerics. Okay, and here are a few energy scales. They are derived from best possible function. Okay, and it comes around minus 78.9 eV, which is very close to the experiment. Okay? The point is that the correlation energy is small. So in the last slide, it was hoped, that okay, we start with this and something, even if we do something wrong, even if we do wrong, as we hopefully that will be small. Okay, although for helium it is small, but for many body system or a real nuclear it is not necessarily small. And small does not mean in no way that that should be neglected, because small things actually contribute to various things like test conditions. Think about a magnetic condition. Mean temperatures are like 300 Kelvin. Okay, it is not even, it is in millielectron volt order, but we know that in temperatures many things happen, many magnetic values are there. All right, so the energy coming smaller does not mean that they are negative. Okay, so the correlation energy, I mean, just to say that it is finite, and for many body system other than two electron system, it is large. So now we are equipped to understand what is density. We have learned how to calculate density, and first thing I have to tell you what is functional. So here are some books that I know that there are various kinds of spectators. So if you are coming from MSc 1 or 2, like you follow this book, and those who are already 2-3 years in PhD and etc., you can follow this book by Richard Martin. It is structured, it is available in Amazon. And for those who are faculty or things like that, you can start for and learn this book. Okay. So, what is density function? So, what I explained so far is calculation of the total energy. Okay, and it was in wave function based or other methods like DMNG or any other method, but they are all total energy, and from there you derive other things. Okay, so here density functional theory is a theory about the energy of electrons being a functional of the density. Okay, so the total energy is actually a functional of the density that we have not observed, but we have actually used it. You will see that to yourself. So what is functional, that we have to first understand. Function and functional are kind of friends. a function associates a number with another number. For example, let us take g of x as a function which is 3x squared. Alright. So if I fix a value of x which is 2, that is I am fixing a number, I get a number 12 for g of x. So this function g of x connects a number to another number. On the other hand, functional, which is a friend of function, connects a function to a number. For example, let us take the same function g of x equal to 3x squared. Then I define a functional which is f of g is equal to integration of gx dx and leave it 0 to 2. Alright. So which is this is the dx and the limit 0 to 2 means the area under this curve up to 2, which is 8. So here the functional attached a function to a number, attached the function gx to a number 8. Alright. So this is what how to do the functional. And I think I will not I will skip this how to take functional derivatives and etc. because we are interested in the part of the test. If you cannot do it or if you do not know, I can send you and write it well for me. I will send that. Okay. Okay. So I have given you this while discussing the artifact theory or studying the equation is given by h psi is equal to e psi, and therefore E I can operate psi star on the left of this, and so E being a kind of number without an operator, so psi star will be normalized. If it is normalized, it will be E, right? So E, as I defined functional in the last slide, E is a function of a function, right? So E is a function of a function because it is using the integrations of this involving psi is giving me E, right? So E is already a function of psi. While this thing is observed, Weinberg and Cohn noted that it is only and only for lowest energy state, which is it is called the ground state, the total energy can be written as a function of density alone. Remember, this is only for ground state. For excited state, the energy cannot be written by a density alone. Cannot be written as function of density alone. It has to be written, but it will be function of wave function, okay, as well, but not as the function of density. So these are the two gentlemen, Weinberg and Cohn. They noted that for ground state, the energy not only can be a functional of the equation, but can also be a functional of the density alone. And we have prior knowledge how to calculate density. Okay, and this is true for ground state. And we have to prove this. So the Weinberg-Cohn strategy is like that. Okay, so in a given system, if I have density, that determines uniquely the potential, because this is how we have defined the Hardy term earlier, right? And for ground state, he says there will be only a single density that will determine the potential. Okay, and if you are giving me this potential, I can calculate psi, and therefore I can calculate energy. Alright. So in general, if you give me nr, then that means density, I will have the energy. Alright. So Weinberg-Cohn theorem says that in the ground state, the electronic density N0 uniquely determines the total energy 0. This 0 is for the ground state. Okay. So this is also known as, I mean, there are various forms of this statement. It says that if nr is not exactly the ground state density, then the energy will be larger than the ground state. It's called radiation density. Now we have to prove this, okay, because this is the heart of density functional theory. All right. So the statement of the density. Okay, let me do this. The statement of the theorem is this. In the ground state, the electronic density Nr uniquely determines the external potential Nr. Why do I call external? Because this depends on the coordinate of the nucleus also. So I forgot to mention probably that you remember this was like Zi by Ri minus capital Ri. So this potential is for a given orientation of the nucleus. Okay, and so if some external coordinate is there, it is a function of the external coordinate, and therefore it is called external potential. Okay. So this is the many-body solution equation, and in order to prove the Hohenberg-Kohn theorem, we write. So I take only this and this as Q operator Q for convenience, and therefore E can be written like this, right? E can be written like this because this is a function of position only, and if I kind of multiply with psi star and integrate, okay, because this is only a function of position only. It doesn't do anything to the wave function, and so psi star psi integrated with all other coordinates will give you density distribution at the position r, and therefore the energy can be written like this. Okay, please do this. Make a source. Okay. Now let us assume that the Hohenberg theorem is not correct, and there exists two different potentials we call V1 and V2 that will give me the same density. Okay. Same density. So by solving the many-body Schrodinger equation, for each potential we can find the lowest energies V1 psi 1. So for psi 1 I get V1, and for psi 2 I get V2 for the potential. Okay. If this happens, so since psi 1 is the ground state of V1, my equation will be modified like this. So this term includes the kinetic energy and the electromagnetic interaction, and this term as the nuclear external term. Okay, and it will be equal to E1 because the variational principle says that it will be either greater than or equal to, and since I1 is the exact ground state for V1, I will have equal to, right? If I use psi 1 for the potential V2, okay, then this has to, I cannot write equal to, I have to, this energy, the energy that I will get V2 will be greater than, this side will be greater than, right? This is the variation principle. Okay. Now if I take difference between these two, this term is identical, so they will cancel, and I will get an equation like this, neutrality like this. Okay. If I start with psi 2 here, okay, if I start with psi 2 here, then I will have, this will be greater than E1, right? And I will get equal to E2 here if I start with psi 2. All right. So doing the same thing, repeating the same procedure as this, I will get N E2 minus V1 greater than E2 minus. Okay, is that clear? I just take psi 1, but I take V2 potential. Sorry, psi 2 and V2 potential. So this term will be equal to V2, and this term will be greater than V1. In that case, I will get this. Now, if I add this two terms, both this and this cancels, and this cancels. So this gives a contradiction. This gives a contradiction that 0 greater than 0. That means there exists no two potentials, nuclear potential or external potential, that will be the same density. That means the density uniquely determines the external potential or the vice versa. So the Hohenberg-Kohn theorem is proven. Now, okay, so we are convinced that for the ground state, whatever Hohenberg-Kohn state, that total energy is functional of the ground state. Okay, it will be functional, but it does not say how this functional is. What is the form of this functional? How does it look like? that you can use it for practical purposes. Okay, so it's like this picture. It is a famous picture also, but you cannot make out anything from it. So this is what we stand now. Okay, so how to construct this energy function for the total energy? Okay, we know some things that we have this external potential term that we have just done. We also have, we know that there will be Hardy energy. We also know that there will be some kinetic energy as well. Okay, this much we know. So we can add term by term all those to this function out. Okay, and whatever we don't know, we say everything else. Okay, so this is what is going on. And this is already started by John and Son. Just after writing that 1964, they started doing this in 1965. In this, they made a very sarcastic and but which proved to be very well is that electrons have some independent particle that somehow produce the correct density of the system. Means if I have a correlated system, it will have a density which in principle I cannot get from independent particle assumptions. Okay? But they said let us have some fictitious particles denoted by this phi I, which will produce kind of correlated electrons. If that happens, so then form of the kinetic energy is same, right? It is minus h bar square del square by twice m, and in atomic unit it will be just del square by 2, and therefore we can have this kinetic energy, right? Okay, there is no minus sign here. So the total energy functional must be having this term, which is external potential, static energy, and energy due to external potential, kinetic energy, and everything else that is called exchange and correlation index. Okay, and like we did in Hartree-Fock theory, we took the functional derivative of the energy in terms of the phi I in case of Hartree-Fock. Okay, here we take as a function of density. Okay? So this is the functional derivative of the of energy functional as a function of density. Okay, and when you change you in principle are changing your i's, but whatever you change, the change must enforce this. So this is the minimization principle for this. And in the few of the earlier slides where I did not describe the mathematics of functional derivative, if we follow those, this condition is a consequence of something called Cohen-Sum equation, which is very similar to that we have got in case of Hartree-Fock equations, except these phi i's are fictitious. Okay, that to be remembered. Physically, their appearance is very similar. However, it represents completely different physical situation. Okay, they said that these are phi i's are fictitious particles or particles that produces density of that of the correlated system. If that happens, that means I have the exact density, then I can have exact answers. Okay. Where this exchange potential is given by the functional derivative of the exchange correlation energy functional with respect to the density at a given point. This is called exchange and correlation potential. And okay, so this is the quantum energy equations, and the heart of the density function theory is to solve this. Okay, so let us go ahead. At this point, I would like to say that he got Nobel Prize for this theorem, which was so simple to prove. In fact, it is 75% of a page in physical degree. Okay, and people, it was so simple that people was actually reluctant to believe that this is correct. But philosophically, symbolically, this is actually exact theory. There is no cooking up. This is exact. In principle, this is exact, but in reality, there are many problems that we talk about. So the quantum theory may be regarded as a formal exactification of Hardy theory, as I have proceeded. With the exact exchange correlation energy and exchange correlation potential, all many effects in principle are equal. Clearly, this directs attention to the functional exchange correlation function. Means how to get that exchange correlation function. We have said that whatever we do not know is included in the exact correlation function. So that means we do not know the form of the exact correlation function. But remember, our hope is that what we are missing, hopefully that is there. Okay. Because we have to start with something. We cannot solve the many-body equation. So we have to start with something. So we started with independent. Then we got the density. Then we got the equivalent potential, which is RD potential. Then we say that no, this function is incorrect. We must go to all the potential. Then we got exchange potential. So we have some example how to calculate the potential and how to calculate the correlation. Actually, for correlation, there is no analytical method to calculate the and it will still depend fully on quantum calculation and experience. Okay. So anyway, so the practical usefulness of ground state depends entirely on whether approximation of functional simple which are at the same time sufficiently simple and accurate. So in principle, we actually have everything we know how to solve, but we know that there are certain things that are still unknown. Okay. So let me go ahead because I was first. And the first approximation to that exchange correlation. Okay, my screen is still blocked by some things and I cannot see some of my slides, some part of my slides. Okay, so it is called local density approximation. Okay, so the history goes like this. When this theory was under build, in 1927, Thomas and Fermi, Thomas and Henry Fermi, these two people already derived the energy from energies in terms of density, kinetic energy, potential energy of electron mass in terms of density, and there was some example that okay, energy could be written in terms of density. Okay, so that was the okay. Let us go to Thomas Fermi. Take that as of that is a homogeneous electron gas, and there is no basically there is no lattice, there is no nucleus, there are only electron gas. Okay, and so it is like h bar k square by Poisson. This figure you can see, and if you take 3 dimensions, so it will look like this, and all the states up to occupied state, which is F, they are all can be expressed in terms of density, and that exchange energy is given by the simple expression. Okay, and it can be calculated. I may have something in the next slide, but these are very simple to derive. So people said that okay, we take this and make this n as a function of r. Okay, and we use this exchange density of that of the homogeneous electron gas. Okay, so that will give me the total exchange correlation energy. If I take this as a density, it is function of moments per electron. Okay, and then this is volumetrical, so that I get the total. So it says that if the system has very slowly varying density, for example, suppose the density profile or density varies like this, as in the blue one in this figure, and okay, the squares are actually a big one. Suppose we make it very small slices, and we say that that the density at when I make it very small, the density at that point is constant. Okay, so but we take the value of this one at that point. So we take the substitute the density of that position at that time and slowly vary. Means I make this squares or the rectangular structure very small, so that within that very small region the density is constant, and we use this homogeneous electron gas this thing, and then we vary. Okay? In that case, the local density exchange potential energy will be given by n to the power 4 third half. This is very easy to figure out because we are using this, but we are making only n as a constant r. So this at the various r, these are different, right? So these are different. So it is not exactly constant, but it will slowly vary. So you have to calculate at each point, okay, which is different, and sum it over, and that will give you the exchange relation. Okay. And the corresponding potential will be given by this functional derivative of the exchange relation and the approximation with respect to the density. And in that case, it is simple derivative of this because the only integration function in that case the potential is this is a very crucial step and crucial step and crucial achievement that one can get some form of exchange correlation. Okay, so here is the calculation how to calculate the exchange correlation potential. Okay, so if it is say electron gas, they are given by plane wave, and the energy is k square by 2m, and so the Fermi energy will be given by kf square by 2, and this is in atomic unit, so the density is n by v, and the Fermi momentum is given by exactly in terms of density. Okay, and this exchange correlation energy. The form of exchange correlation energy. This we can obtain from Hardy-Fock theory. Okay, this is see Hardy-Fock theory do not take care into account the correlation, but it takes care of the exchange. Okay, and this is the form of the exchange energy. And we substitute in this and perform the integration. Okay, because it is electron gas and it has a continuum energy level, so some can be replaced by integrations and so on, and therefore it will take the form of this. And you notice these are in terms of r minus r difference in this thing, and you express this in dimensionless variables. So you substitute this, and you get a very simple expression of exchange correlation, which is proportional to the k to the power 4. Kf to the power 4, and kf is kf to the 4, and kf is this. So that is why you got in last slide this n to the power 4. Okay, so it can be calculated exactly, and this constant is the dimensional constant. If you cannot calculate, write to me. I will send you this slide. Because this constant was calculated by in 2000. Okay. So what to do for the, so we got the exchange, what to do for the correlation energy. Honestly, for correlation energy, there is no energy for even for and it depended on the quantum orbital. Okay, and then it was actually fitted with this kind of expression. Okay, where RS is the radius or the size of one electron by its volume. So this is high density and low density unit. So this is fitted with the quantum results. All right. RS is related to the density, like n is equal to 1 upon 435 RS cube. So if one electron is treated as a sphere of volume 1, then the corresponding volume of RS is 4.5 R3. So that gives you yes. Okay. And so this is how correlation are done. Even today, correlation energy is a problem. All right. So we have learned local density approximation. Okay. So in the Hartree-Fock approximation, Hartree approximation, not wrong. Hartree approximation exchange correlation was not there. Okay. The exchange correlation, if you include, that takes care of something called self-interaction connection. What is self-interaction connection? Okay, it's a look. Our strategy is that we have some phi i's which are fictitious. That gives you some density. Because of the density, it produces an electrostatic field. The electrostatic field will also have effect reverse effect on each electrons, right? So that's called self-interaction. Mathematically, the uh, electron repulsion term is something like E square by Ri minus Rj, I not equal to J. When you try to write it in terms of density, you include I equal to J term and then minus I not equal to J term. Okay? So there is a single term which is I not equal to J term that contributes to the self interaction. I hope this is clear. Physically, what I have said earlier is that the orbitals gives you some kind of density. That density produces density is charge density that produces field as well as exchange field and so on. And therefore, they will have effect on individual electrons, which is called self-interaction. Okay? And managing properly the self-interaction correction is still a very difficult work in terms of it is still developing in terms of theory. Okay. So what is this LD approximation exactly is and where it is valid is written here. Okay, I have discussed what is so you define the exchange correlation density which is uniform, okay, and you get the total exchange correlation density as a function of density. Okay. The LDR calculation is good if you have uniform density. In fact, it's exact for uniform density and slowly varying density for in space. The criteria for validity is that the fluctuation in density, it's not constant. We know that the aerial system the fractional change in the fluctuation, which has the dimension of inverse length, must be less than the fun vector. Okay? In that case, it is shown. I am not showing those details. These calculations are done by Cohn and Sam, and later on by Purdue also. Okay? And so this is a case is some kind of screening vector of the Thomas Harvey model. That should satisfy this. Okay. And when I was showing the correlation energy in the last slide, actually that was done by Wigner. Okay. So after fitting his result from the quantum Monte Carlo results, he arrived at some expression in terms of expansion in terms of RS, and this exchange correlation as a functional means this is the density exchange density. 1930, it was derived by Wigner as well as by Dirac, who have some form but not exactly the same. Okay? And then, but they agree in some high density and low density. High density limit, which means RS tending to 0, so that so the density will become large. As I said, n equal to 1 upon 4 times pi r. So if RS is small, density is very large, and density is given by this characteristic constant. There are methods to evaluate those. And the low density limit, it gives like an exchange, because the exchange form is already given by here. This results matches with quantum. or correlation, we still today rely very much on quantum and experience. Okay, so this is now actually the heart of the density function or the essence of the density function. So uh, you are given me some capital Ri's, the position of the nucleus. Actually, it is not essential in modern density function. That can also be the structural optimization can also be determined. But let us say that either you determine the structure of optimization. Today it will not be possible to describe the method of optimization. You know, density functional theory is a ocean, and you know, uh, you know, lakhs of papers have been already published, and so many people have worked, and in 1 hour you cannot describe them. So, but in any case, um, so either you experiment from some external experiment, you already get the structure of the material, so you get the RIs, or you determine. So that gives you the external potential. So given an external potential, you have a test density because you need to determine density. But anyway, you have a density. So you get an initial density. From initial density, you have the Hartree potential as well as the extreme potential. So you have the total potential, and then you have the basically you have the Poisson equation, and you solve this orbitals. You get a density. Check with this density whether your total energy is the same as you started with. So obviously, it will not be the same. So these solutions you take as new density, go back here, again produce all the potentials and new pies. So if you will get new potential, you get new pi, you get new density, and therefore again you get your energy is function of density. So you know again the density and total energy, and you check your earlier energy, total energy is this the new one, and when you make a cut off, the difference is very small. You stop, and then you can calculate the difference. So this is the estimation of the density. So there are many other things that are associated with density. Okay, so another step is called plane waves or pseudo potential method. Okay. So okay, we are supposed to solve in density functional theory some equation of this sort. Okay, so all the potentials are included in this video. Okay, so numerically, after all, it is a second order partial differential equation. To solve any partial differential equation, you need boundary condition. Okay, and if same equation you are solving, but for different conditions. For example, if it is atom, anywhere, or molecule, or quantum dot, or nanowire, or nanoscale, which are confined. Nanowire like one dimension, nanoslab is like two dimensions. Okay, so if it is in one dimension for a given y, and z, okay, you have to find the value at plus infinity and minus infinity. Okay. And there, normally this is for localized states because atomic states are localized molecules of similar quantum loss confines and hence they are localized states. In those cases, you take the boundary conditions as that the phi is 0 at x equal to plus minus. This is for localized state. In case of solids or liquids, which are extended system, okay, in that case you take something called periodic boundary condition or bond carbon boundary condition. Bond carbon, there are two countries. They have contributed to this tree such that uh, that at any point, depending on the periodicity or lattice constant, which is this A, the function repeats itself. not only the function, is derivative also. Okay, so this is what is it's like if you think in terms of one dimension, for example, I have only taken x1, it should be also in y and z for a three-dimensional periodic system. Okay, like if you take a ring, that means the last point, okay, is same as the beginning point. In similar way, this is true for any point. Okay, so this is true for any point. So this is what is the, that means it is infinite. So this is how you mimic infinite dimension. This is not exact for, but if you take your unit cell big enough, this is almost close to the real. I talked about in the beginning when I talked about my model calculations that we will do later. I told that I could work only on 12 sites. Okay, but 12 sites I take periodic boundary condition, so it mimics like the infinite system. Okay, so let us go ahead first. So maybe I skip this one, but anyway, what the normal codes, codes are written for periodic systems, okay? But not necessary that we cannot do it for molecules or amorphous systems. You can do calculations for molecules as well as for amorphous systems. Let me just mimic for molecule, for example. So you can keep the H2O molecules in some arrangement sufficiently large distance so that their wave functions do not overlap. Okay, so you can create a lattice. You can check that if A is let's say 5 angstrom, what is the result? You need to do 7 angstrom, 10 angstrom, 8 angstrom. So as you make this A larger, the wave function for a single molecule H2O here will not overlap with this or this or this or this, and they will be same as a single H2O molecule, and that kind of calculation you can do with. Similarly, you can do for amorphous, but let us not discuss amorphous today. It is a bit difficult, but you can do it. Okay. So, what is the plane waves about? Okay. Plane. So, after we have got the strategy how to do the density function theory, there are many numerical issues, numerical problems. Okay, and you have to optimize which one we will be able to solve faster. Okay, so one thing is this. This is no way an approximation. This is exact because when you have a periodic system, okay, periodic potential, so the states are also periodic. Like my phi must be periodic, right? So this is what that periodic boundary condition that we discussed in the last slide. All right. Okay. So you express your phi x in terms of Fourier expansion. Any periodic function can be expressed in terms of this Fourier series. Right? So this is exact. And so in some point I discussed about this silicon problem that you have to discretize the state and space and evaluate your each point, etc. That will not be required at all in the and that is the point. Okay, so here is the plot of the real and imaginary part of this things, okay, which is nothing but cosine and sine functions, and this then automatically satisfies this periodic boundary condition. You can check this. Okay? Not only the function itself, but it's but also its okay, so it becomes a continuous function. So what happens? So what happens actually numerically? So you have the second order partial differential equation, right, in real space. Numerically, doing second order partial differential creating derivative is very difficult. You know, second order derivative is difference of derivative, right? So don't quote me for this. For a given point, it takes 70 points to calculate. So So it is very slow and very also inaccurate. Derivative, is very inaccurate also. Okay, so we go to actually momentum space. So this is nothing but Fourier transform. We go to momentum space. So reciprocal space, in fact, and so your reciprocal wave vectors, as you know from your solid state physics, is given by this in 2 and 3 dimensions, and then you define your G vector or reciprocal lattice vector in terms of 3 integers, with this 1, 2, 3, with this formula. Okay, and you can like your real space. Okay, of unit cell, you create a reciprocal lattice momentum space, and in that case, your this function, which was Cn to the power twice y and x by a, will be written as e to the power I g dot r or g is like this. Okay, so then your phi i's own sum function. That means you are expanding your own sum equation in terms of players. That is why this is called playing. So what is the advantage? What is the advantage? You have actually converted when you put it back to the differential equation, the own sum differential equation. This equation, when you substitute this partial differential derivative thing becomes an algebraic equation. Okay? In terms of the coefficients. And you have got this equation. And therefore it becomes a matrix equation. So this you can write in terms of something matrix times CIs is equal to epsilon 1 to 3 in terms of the CIs and the sum of that expression, which is much easier. Okay. The next thing is that how many CIs should I take? How many CIs should I take? So here is an example. If you take, for example, n is equal to 1, so the first term in this, so you take twice pi a only, and then you can, you do not sample the momentum space very nicely, but as you take larger and larger n's, okay, so that means this is third term in the series. And you can actually sample the finer details of the given space by this IR. Okay. But then, how many should I take? Okay. How many should I take? That is decided by something by the. So this is like free particle, right? This is like playing wave, and this is like free particle. So its energy, kinetic energy, or total energy is all kinetic energy should be given by the Cg square by right? So inverse square k square by myself, and so this is called. So this is this Gmax, highest Gmax. This is called the cutoff. So those who are doing already against they know that they are using some cutoff, energy cutoff. Okay, so that cutoff is given by this kind. Okay, all right. So now there's one more thing, that one more simplification or important simplification that we do, that is called pseudo potential. All right. So what is pseudo potential? Here is a calculation for silicon, as we have mentioned in the beginning. So silicon atom, single atom silicon state, and here is the periodic table. It is here. It has 14 electrons, and if you calculate all the energies, here something is blocked. So this is for the s electron, 1s, and so the other electron energies are here, 2s, 3s are here. So 3s, 3p is very close by and small. So if I take, let's say, 2 silicons, if they are forming any bonding between silicon and silicon, this will have no role. This will have no role because this is so distinct, right? So only these labels may interact or form one. Okay. So this is the idea. Something like you choose only valence electrons. They are only responsible. Not this. They are very largely bound, so negatively bound states, and so strongly bound they cannot form bonds. All right. So this is the state. So what you do? There is something missing. One slide is missing. Anyway, so this is the plot of different orbitals for silicon. Okay. So this is the 1s, 1 state, and then this is 2s black, 2p also black, and then 3p state, and then the 3s state. And this distance that I mark is a silicon bond, something more than less than 4.5. So if I plot density of this orbitals, so you can find out the density looks like this. So in the core region, you have this thing, and when you are supposed to have some bond, so this is supposed to be the bond length. The bond length. The density is important density comes from the valence electron only, and the core levels are pushed towards the nucleus. So they are not really, they will not play any role in form chemistry, okay, or the chemical properties. So this is the idea, and so what to do? So uh, this black line, this is the silicon 3s. Okay? The black line is the exact orbital function. Okay, looks like this. And suppose the sampling idea that I have shown in earlier cases, earlier slides, with particular delta R, I could feed this part, and then when there is a sharp change in the wave function, there I will have definitely have some problem. And when it changes sign, in the core region, perhaps, okay, it will be very difficult to sample this thing, right? It will be very difficult to map this, okay, and I may lose the sign change. Okay, so the thing is that you try to so anyway we are going to, let's say, leave these courses because they are not responsible for bond formation or chemical sciences. Okay, so you sample in such a way that that means you fit your actual or the exact orbital in such a by some pseudo wave function or pseudo state that is construct such that it matches exactly, okay, outside some region, but I mean, it may not match this thing, and if you can uh, avoid this sign change of the what comes from the oscillation of the wave, it's too many near the core like this. Okay, so calculate the strategies like this. Calculate quantum wave function in presence of core electrons. This wave function is typically referred as all electron function. Beside a radial cutoff RC, that is the radius, which sets the boundary region between the where the wave function is to be modified. Okay, so this is called pseudization of the region, which I have shown in the last figure. Inside the pseudoized region, replace all electron wave function by a smooth one. Okay, and simple polynomial. The new wave function is chosen so as to give the same electron density as that of the all electron in the outside region. Okay, so if you do this, so this is shown by the blue graph. Okay, so this was the let's say radial this thing equation for solving the equation or some equation. Okay, for 3 years I have just written it down. So you you change the exact 3s by the pseudo wave function. All right, and this is in blue because you do not know what is the potential. You do not know what is the potential. So, so ideologically, because you have already fitted this UHDS pseudo function, you can calculate the d3s. Okay, following the prescription that I have given in the last slides. And in that case, you will get so this is minus 4 upon r minus this is the charge minus data upon r. Okay, and the pseudo potential is good like this. So it is not same in the code. Okay, but, but it is exactly the same thing outside the code, which is let me skip this. So these are the things that you face in doing density theory, and and as I said, that the main challenge becomes how accurately you can calculate the exchange rate. Okay, and what are the other steps in terms of the wave function that I have said. So LDA was one of the cornerstone, okay, one of the first important step, but you have in LDA in many cases fails, and one has to go beyond LDA to have a meaningful performance. Okay. So LDA I already explained. LDA, in LDA you expand or you have you write your energy functional in terms of the density alone. Okay, so let me show a practical thing which for different molecules as in the x-axis of this figure is plotted for two approximations. One is exactly in an experiment, and another which is called PB. Okay. I cannot see my slide properly. It is for the both K and their function. Okay, so it is obviously below 77865. And the energy exchange correlation energy is already expressed in my earlier slides like this, in which you can write your exchange correlation density of in terms of density alone. Okay, energy density in terms of density alone. The next step is to include functional in which not only have density but the gradient of density also to take care of the variation in density. Okay. This is not trivial. In fact, it took a very long time to get this change. Okay, and I hope I have. So this has a background. Actually. This has a background. Parallelly, there were other calculations. For example, other methods of calculations, and there are expansion in terms of the gradient of density by other methods, and there are improvements. So it was anyway, this is called atomization energy. Means if you have molecule and then you separate two atoms, what is the energy that is required for atomization energy, and you can see that so this is done by PV, this three persons, so they are exchanging correlation functional is called PV, exchanging correlation functional that essentially takes care of the radiation density also. In fact, this is a modulus of the delta analysis. What we are using it is a module of delta NR. Okay, and the expense in numerical is not that difficult. It takes almost similar time, computer time, etc. Even if you do GGA, but the results are better. Okay. There are many results that I could compare, but I wanted to give the philosophy or the idea behind the density theory. And right now we are only revising on the exchange correlation function. And you can see that if I do LDA, the error in atomization energy is much more compared to Uh, Even PB is not sufficient. So what happens actually? There you have materials that contain sometimes they contain very localized orbitals, okay, and they fall very close to the formula. For example, transition metal oxides or rarer materials which have 4 electrons, 5 electrons, heavy fermion, for example. Okay, and in that cases, for example, I have presented here with this particular color. They have 3D this thing, and these are having F electrons. Okay, rare earth atoms are having 4 electrons. So for those particular atoms, the variation in density is very strong. LDA or GGA. GGA is slightly better than LDA in terms of accuracy in numbers. Okay, so it takes care of some variation, but it can if your orbitals are very sharp or localized in particular position on R, so the corresponding density variation is enormous. Okay, so the idea was by these 3 scientists, and Jamin and Anderson, they said that this the density variation for this localized orbitals are not taken care by either LDA or GGA. There are many variations of TDA. Many variations of TDA. Everything is not possible to discuss in one talk. Okay. So they said that for those, we must add on-site Coulomb difference for those localized orbitals. This is called Hubbard, John Hubbard, who discovered this different context already. That models are already available, as I showed some of my earlier words. So this is called that those are called DFT plus U or GDA plus U or LDA plus U calculations. So the idea is that you have to modify exchange correlation taking into consideration the sharp density change of those particular localized orbitals as well. Okay. Okay. So uh, are you being able to listen to me?
Uh, yes, sir.
Everything is all right?
Yeah, there is one more thing, sir, that you want
Yes.
to add. We
Yeah.
have another talk at 4 o'clock, so could you please finish your talk?
Okay. So I'll use 2 or 3 slides just
Yes.
to give the idea.
Sure, sir.
And finish. Is that okay?
Yeah. Yeah.
Okay.
Okay, sir.
So,
Please.
okay. So what is U is given by this expression. In fact, this is not the U, not all of the U. When both I is equal to I prime and J prime is also I prime, that quantity is called. So this is the general expression of Coulomb correlation, and this is so this takes the form of Q and I up and down. Is called Howard term, okay, and they are added in LDM plus Q. Since I do not have done time enough, so the LDA plus Q term is functional is okay, and so again, you do the same thing, including the correlation term of the for the localized state, and which turn to show that it affects the conduction and creating a gap between these. Without this, you are getting metal for which are supposed to be instrumental. Okay. So let me quickly pass this. So this is one example using PBUC metal for this iron oxide, but when you use PBU plus, you get an insulator. Okay, so then next came the hybrid functional. Okay, so the question was that I mean gaps were not coming from polymer, etc., etc., and therefore there are many improvements. So you add Prof exchange. Prof exchange was very difficult and expensive because it is non-local, and as I said, the numerical calculation goes of n square, not n, and so you make some combination of these. So and then there are HSC and etc. So there are days of IV functional and etc. So I quickly finish this. Then when other many body ultimately this exchange correlation was changed by something called GW approximation, and so that improved things. Finally, this is the ladder. Means you start from 30, which does not have any exchange position. Then you go to local string density. So I didn't mention about this. So it is same as LDA, but you do it for both up and down strings. Okay, and then you do GGA, which includes delta N also, like delta N up or down R, along with N up and N down. And then you go to meta GGA, which takes correction in kinetic energy. Okay, and then you come to hybrid function now, which is this parameter is still free parameter, but this day the best functional has already come. It's called scan potential, and this agrees with many results and so on. And after even above this, you have RPA and so on. So I stopped this because there is no time. I hope I have given you the idea of density functional theory. I'm sure many things are not clear, as one thing is we are not communicating to each other, and another thing is that I mean I do not know the level of the participants. So thank you very much for my questions.
Okay, thank you, sir, for the informative talk. And we have received lot many queries, but unfortunately, as we are already running late, we cannot take all of them. So we are taking one or two queries. So students are asking, is it possible for outsiders to use computational facilities at RRCAT?
There is no straightforward answer because we ourselves are already burdened with. But
Overloaded.
you can find, you can find someone to whom you can work with, and he can help you submitting your jobs.
Okay. Okay.
But
Then
outside, sitting at your institute, you can.
Okay. Then another question is, can we calculate nonlinear optical parameters using DFT?
Yes, we can do non-linear optical properties, but the things become very complicated. There's something called chi3, etc. You can calculate this.
Okay. Okay, sir.
But you have to go to active time dependent DFT, not this option.
Right. So, okay. As we are already running late, let us thank the speaker, Professor Ghose, for his valuable talk. And I hope the participants will be benefited by his talk. And once again, I thank you, sir, for accepting our invitation and delivering this informative talk to our participants. Thank you, sir.
Thank you very much, sir.
Thank you so much. Thank you.
Okay. Professor Ispal, Dr. Ispal can now please proceed for next session.
Yeah. I'm going to log into the next session with talk on magnetic measurements of materials. Okay. So,
Thank you all.
that. Yeah.
Thank you.